are all out of whack. I'm planning to, like the numbers don't match up with the problems and stuff. I'm planning to fix that, but I don't know. Maybe, hopefully I can get to it later today. But anyways, in the meantime, anybody want to see any of those problems done? The vector problems that you've been assigned, anybody want to see any of those? Confused about how to do any of those? No? Okay. Yeah, I'd be happy to do.
A side note on that, when on Thursday, are we sending in a packet of papers for that?
A week from Thursday, right? A week from Thursday. Yeah, you're just handing in a packet of papers, and I would really appreciate it if you could do it in the order that they are assigned, which sometimes will not be linear, So it just makes it so much easier for me to find stuff. But just everything that's assigned in one assignment, just staple it all together in one thing. Okay. Yes, thank you. I want to clarify that too, because when it gets turned in assignment by assignment or like in a different order, it's just so hard for me to find what I'm looking for, so. Are you still looking for problems that you might want to see done?
Probably.
Okay. Yeah. Let's that one. So number 11. It looks something like this. So why did I even draw this body? I mean, I guess it's really a similar question when all you care about are the points. I mean, the reason that I draw the body is because the setting that you're going to have to do this in this class always has to do with relating one point on a body to another one. So I'm just trying to make it look like the problems that are the way it's going to come up. But I think the points were like A was here and B was down here.
Yep.
And this length was the height. Okay. And then this 3.2. And we wanted to find the vector first from A to B. And second from B to A. Remember, to find the vector from one point to another one, there are two ways to do it. If you're already given, or it's really a special, it's easy to find the coordinates of A and B, then you can just take the coordinates of B and subtract the coordinates of A, and that gives it to you. If you're not already given the coordinates, then put the coordinate system at the starting point. You're not actually putting it's just sort of you're just imagining this. You're not really changing where the coordinate system is. It turns out where the origin is doesn't even matter. But think of putting the origin at the starting point. And then just calculating the coordinates of the ending point. So if this is the coordinate system, what are the coordinates of that point B? It's in the positive x direction 3.2, in the negative y direction 3.5, and so that's that vector. And then so this is the vector 2b from A. Then the vector 2a from B. You can do on its own by imagining the coordinate system at B and calculating that vector. Or since we already have from A to B, it's just the negative of this. So, it's negative vector 2B from A, which is negative 3.2, positive 3.5. Yes, I know that the question you asked was a very short question, and that was a long answer. But that's why, because the reason I'm drawing these bodies in at all is because that's how they're going to appear later. And I think it's a good habit to get into to sort of sanity check these components. You can always do that. I mean, does it make sense that we have a positive x component and a negative y component going to B? Yes, it's in the fourth quadrant, so that makes sense. Does it make sense going to A from B that we have negative x, positive y? Yes, because that would be in the second quadrant. Any other? Yes?
How much of that work do you want us to show on the homework? Do you want us to draw the diagram again and then show that step, or? I don't really care on this if you show, my general answer for this class is I want you to show a lot of work, but this isn't something that you have to show any work at all. But one thing with showing work that you should think of for this class and probably every class is think of showing work as like an insurance policy on making dumb mistakes. Because if you make a dumb mistake inside a thought process where you don't show any work, you get that whole thought process marked wrong. You know what I mean? If you show your steps and make it and to the point where someone can identify where you said, oh, they accidentally added whatever, then you get credit for most of that stuff and only get marked out for the little thing, So so that's the reason why, that's the main reason you would want to show work, is so people can identify exactly what you got wrong and give you credit for the stuff you got right. Like in the extreme example, if you get asked a long engineering question and you put down the answer 3.5, and the answer is -6, you get 0 points on that problem, If you do essentially the right thought process and put down -3.5, you get 9 out of 10 points on that problem or whatever, Okay, any other vector questions? Yes? Sure. I don't know what that is, though. Anybody in the front row have those problems sitting in front of them? Thanks. Number 4. Okay. 1, 2, 3, 5, 2, 1. So the vectors are 1, 2, 3, and 5, 2, 1. And we want to come up with 2 vectors. Oh, does it say 2 unit vectors or just 2 vectors? Give 2 unit vectors where each one is perpendicular to both of these. Tried to clarify that, and somehow I made it sound more confusing. Each one of these 2 vectors is perpendicular to both given vectors. Okay, well, the key to this, and this is I almost can't think of any vector operation that's going to come up more often than this in the rest of your mechanics classes, is the cross product gives you a vector. The cross product of 2 vectors gives you a vector perpendicular to both of them. So anytime you need a vector perpendicular to 2 other vectors, you're going to do it with a cross product.
And that's true, so 1, 2, 3 crossed with 5, 2, 1. And that's equal to negative 5, 2, 1 cross 1, 2, 3. Gives a vector perpendicular to both. Anytime you need a vector, like anytime the word perpendicular comes up in a mechanic, I mean really in any class, the first thing you should think is cross product, and the second thing you should think is dot product, because you know the dot product of two perpendicular vectors is equal to 0. So take the cross product of, and it doesn't matter, you could do 1, 2, 3, 5, 2, 1, or you could do 5, 2, 1, 1, 2, 3. They're opposite directions, but what do you get if you take that cross product? Okay, so this one is negative 4, 14, negative 8. Okay, so that's perpendicular to both, but it's not a unit vector. So to get a unit vector, we want to take a unit vector in this direction, right? If it's in that direction, it'll still be perpendicular, but it'll have a length of 1. So we'll call this u. And then the magnitude of u is 4 squared plus 14 squared plus negative, those negatives don't end up mattering. And what do you get for this?
276.
And then square root of that. So,
Oh, I just put square root of 276.
oh, okay. Anyone have a number for that? I like to get round off error into my problems. 16.613. And then, so the unit vector is equal to 1 over that length times the vector. So what's negative 4 divided by 16.613? What? Really? Yeah. Point. I've heard like 30 different answers.
Yeah, I got 0.241.
0.241, okay. And then 14 divided by? Okay, that sounds good. You know those things that you all have sitting in front of you, those do these calculations. That's what those are for. And then negative 8 divided by 16.613? Okay, 481. And so then the other one is, so that's one vector perpendicular to both of these, unit vector. And so the other one is just the opposite direction. And so it's 0.241, negative 0.843, positive 0.481. Any questions about that? Quick, somebody give me the magnitude of this vector. Yeah. Trick question. So that's the idea of these unit vectors, is they have length of 1, but they have a direction. You can think of it as just a pure direction.
time he give us a problem, like we're supposed to find the three things, right? The direction, point B to A or A to B, and the magnitude or the length, and then the unit vector.
Yeah, well, only if it asks, yeah, if it, the ones where, so we did this one and we didn't have to calculate the unit vector because we were just asked about a vector that goes from one point to another. But if you're asked about a vector that's in a certain direction with a specified magnitude, then you need to turn that vector that goes from A to B into a unit vector by doing what you're saying, and then multiply it by the magnitude. So, like for example, it didn't ask for this in this problem, but what if this problem had asked for a vector with a magnitude of 80 that's perpendicular to both of these two vectors? How would you do that? That's exactly right. So if you wanted, let me just say the question again. So say you're given these two vectors, okay, and you want a vector that's perpendicular to both of those and has a magnitude of 80. The way to go about doing that is to first come up with the pure direction, which is what we already did. That has a magnitude of 1. And now once you have that unit vector, multiply it by 80, and you have something that has now a magnitude of 80 and the desired direction perpendicular to the other two. Okay, so that's, and here's how it's going to come up more often for us. How about what is a vector that's perpendicular to both of these and has the unknown magnitude r? You know, how would you get that? You'd calculate the unit vector that's in the desired direction, this, and then you'd multiply it by r. And so your answer would be negative 0.241r, 0.843r, negative 0.481r. And that kind of stuff is going to come up all the time. Okay. Yes? Yeah. This positive 14. Oh, let me make sure, but I think it's because the y component is always weird. It always has that negative. And so it's 1 times 1 minus 3 times 5, but then negative of all that. And I think I mentioned this before, but there's no reason to beat yourself up by having to do these by hand. All of your calculators either do this already or can be programmed in a very easy way to do these calculations for you. Getting your calculator to do stuff for you is a very easy way to avoid mistakes, you know. So if you don't know how right now to get your calculator to do cross products, come talk to me in office hours or after class, if not too many of you, you know, if, and I can write a quick program that that'll just do this for you. Yep.
Oh, there is. The other calculation at the bottom. What was that?
The question is find 2 unit vectors perpendicular to both of those. So one I did using the cross product and then took the unit vector. And then the other one I just took the negative of that because, you know, just visually, if these are your 2 vectors, you want to find 2 vectors perpendicular to those. One is this way, and one is just the opposite direction. Okay.
Why do we multiply it by r? That is like if they ask us to find a parallel, we multiply it by r.
Why do you multiply it by r? So, what's a vector in the direction of negative 0.241, positive 0.843, negative 0.481, with the magnitude of R. Okay. That's equal to negative 0.241 R, positive 0.843 R, negative 0.481 R. And you can see, do it once, and you'll just see how it works. Calculate the magnitude of that vector using the Pythagorean theorem thing. You'll see that the length is equal to R. The reason that's going to be such a useful thing to us is because we'll have problems where so it shows up in the following way. Say this is part of a free body diagram. You have a vector that, an example of this is like a cable tension or something. You know the direction that the force is, but you have to calculate the magnitude of it. Well, you'd look at this at first and say, like, I don't know what that vector is. So if you don't know what the vector is, you think, like, I have to calculate all three of those components or two of those components in 2D. Well, it turns out you don't have to calculate. That would suggest that you have either 3 in 3D or 2 in 2D variables to solve for. That means you need 3 equations or 2 equations. It turns out you only need 1 equation to solve for this because we already know the direction. And so by using the unit vector and multiplying it by an unknown magnitude, this variable, we can represent this vector with a single unknown, and we only need 1 equation to solve for it. That's the usefulness of this in this class. It'll come up all the time, and it'll be more clear as when we get to real examples. But this kind of calculation we'll do all the time. Yep.
So when you're given two vectors and they're both 2 by 2, so when you're asked to find the cross product,
Yeah.
do we include the z component?
Just the z component, make it 0. Yep. And so let's imagine this for a second. So let me try to draw this in sort of 3D. Okay, there's the xy plane. X-axis, y-axis. And let's make up any 2 vectors in this xy plane, okay? What are 2 vectors that are perpendicular to these? The answer is always the same. One in the positive z direction and one in the negative z direction. If you have 2 vectors that live in a plane, the perpendiculars are always always out of the plane, the normals to the plane. And so we'll see that when we're doing 2D stuff, where all of our force vectors and stuff are in the xy plane, all the things that we calculate using cross products have only z components. Any other questions? Yep.
If the cross product in 2D goes into the third dimension, then what direction is a cross product in 3 dimensions?
You don't know. It couldn't be anywhere.
Okay.
Which is why this is probably going back into too much detail of your memory of Physics 1, but we'll go more into this kind of stuff in this class. But if you have like a rigid body problem, so remember the moment equation. the moment equals I alpha. If you're doing problems in 2D, the moments and the angular acceleration only have z components. Okay? You just have a single moment equation if you're doing a problem in 2D. If you're doing a problem in 3D, that moment equation requires all three components because you're taking a cross product to get that moment, and the cross product of things that live in the full 3 dimensions can be anywhere in 3 dimensions. Any other questions? Yep.
Do you still have a quiz there?
Yes. So I'll hand out the quiz at 10:30 or 10:35 or something. 13, yeah. Yeah, you know, okay. 2.5 meters long. Okay, yep. So we have a rigid body that makes an angle of 10 degrees with the horizontal. And the length of this thing is 2.5 meters. And, you know, the way this is going to come up in statics problems is this is a rigid body with, like, say, a joint here, and we're trying to calculate, so say that's A, and this is B. And what does it ask for, the vector from A to B? A to B and B to A, okay. Well, there's two ways to do this. One is if you know the coordinates of the 2 points, you can subtract, and the other way is, since we aren't given coordinates, we'll put the coordinate system at the starting point, and then we just have to represent the coordinates of that point B. So the coordinates of that point B are just 2.5 times cosine of 10 degrees, sine of 10 degrees. What are cosine? What do you get for this? 2.46? 434. Does that pass the smell test? Yeah. It's in the first quadrant, so you know that both components have to be positive. That angle at 10 degrees is less than 45, a lot less than 45, so you expect it to be farther in the x direction than in the y direction. And then for B, now that we've already done this one, might as well just take the opposite of that, although you could go through this whole process again. Let's go through the whole process again, because I like to waste time. No, but actually I think this is helpful because it's in. Oh, yes, you can. You have total freedom to choose.
It's better to choose it at A because we have coordinates.
Well, if you're going to do it this way, this really, think of this as, to do this calculation of a vector from A to B, you're not really choosing where the origin is. This is just like a way to do this problem. The real coordinate system you could think of as wherever you want. Okay? So this is a calculation approach. So where you put the origin wouldn't change this answer. The only thing that would change this answer is changing the orientation of the axes. You can do that too. You'd get different answers, but they'd still be right if you thought of it the right way. Okay, so let's think of it again. So here's A, here's B. This angle is 10 degrees. And so now we want the vector 2A from B, so we'll put our coordinate system here. This pretend temporary coordinate system. And what you have to recognize is that this angle is 10 degrees. And so now a counterclockwise angle from the positive x-axis to, so this is the vector we want. So what's a counterclockwise angle from the positive x-axis to our vector? What's that angle, theta? 180 plus 10 is 190, yep. So theta is equal to 190, and so you can just do this vector as 2.5 times cosine of 290, sine of 290, and you get negative 2.46, negative 0.43. Yes, thank you, 190. Round off error. Okay, so and if you did that calculation, you'd get this, which is exactly the same as the easy way of doing this, just recognizing it's the opposite. Yep.
What happens if we choose the angle because it's 90-10 and we choose it otherwise over there, the angle from B to the y-axis?
To the y-axis?
Yeah, yeah.
And you recognize that this is 80 degrees?
Yeah.
And do it that way? Okay. So, oh yeah, right, because I think that's a way a lot of people would think of it. You'd think of this as a right triangle. You know that's 10 degrees, so you know this is 80. Well, if this angle is 80, then you can think of, you can go clockwise, go minus 90, minus another 80, so minus 170, which is the same thing. Or you could go counterclockwise and think 270, backtrack 80, which gives you 190. And so, yep, it works the same. Any other questions about any of these vector problems? I'm happy to spend a lot of time on these vector ideas because they're kind of the, I think it's a really key thing to be comfortable with this stuff for what's going to come up. Yep.
I don't know what the problem number is.
Mhm.
I think it's 14.
Okay.
It's the problem where you have a beam and a cable.
And a cable. Yeah.
How do you tell which one in context is the force that the beam is acting on?
Yeah.
The beam is acting on the wire and the beam.
Yes.
The wire is acting on the beam.
Yep.
I worded that terribly. But
I know exactly what you mean.
I found myself having a hard time figuring out which force is which.
Yeah. Okay, so we have the beam. Okay. 14. Okay, and then the cable goes from here to here, and it gives coordinates of those 2 points, right?
1, 1 and 4, 2.
So this is 1, 1. this is 4-2. And it asks like, and it gives a cable tension, or it calls it T, or what? Okay, so we have a cable tension T. So what's the force applied to the beam by the cable? And part B, what's the force applied to the wall by the cable? Is that right?
Something like that.
Well, these cable forces are pulling forces, and so they're always parallel to the cable, and they always go away from the object that you're applying the force to, the object you're isolating. So, so for part A, since we're talking about a force applied to the beam, we know that that force has to be in that direction. And it has a magnitude of T. And so in this case, we're given the coordinates, so we're going to use that other approach to calculate, a vector u that goes 2, 4, 2 from 1, 1 is equal to 4, 2 minus 1, 1. So 3, 1. Okay, so that's a vector in the right direction, but it's the wrong magnitude. We want the magnitude to be t. So first we're going to come up with a unit vector in this direction, which you do by taking the magnitude so root 10, and then the unit vector is 1 over root 10 times that vector, so you get 3 over root 10, 1 over root 10. So now that's a unit vector in the correct direction, and then the last thing you do is you just have to multiply it by the magnitude you want. So the force on the beam by the cable is 3t over root 10. We're just multiplying it by t, and then 1t over root 10. Yep.
Is it the right notation, like how you have the force on B by C, just have like the force of BC?
Yes.
Okay.
And we just haven't talked about it yet in this class, but that's how we'll do it.
Okay. I just wasn't sure if it was that way
Or the opposite. Yeah. Okay, want to hear what... It's confusing. I mean, it's just hard to remember. And then also, different engineers and different physicists use opposite notation. So, like, you might have a physics. So, in this class, we're going to call this FBC. And then later, there's a good chance you'll take a physics class. It's more common in physics to do it the opposite way, more common in engineering to do it this way, where they'll call it FCB. And then you'll spend the rest of the day punching yourself in the face, in frustration. But there's nothing I can do about that.
We don't know what the tension is. We just multiply it by the tension.
Right. We don't know what it is, and the idea is we'll use Newton's laws to solve for it later.
Oh, okay.
And so then, I'm not going to go through those steps again, but for B, the force that the cable applies to the wall, it always, then we're talking about a force on the wall. So it's parallel to the cable, away from the wall, so it's that way. And you do it in the opposite way,
Okay.
which ends up just being the negative of this.
Okay. I just have a hard time visualizing how that force works direction-wise.
How it works direction-wise. Yes, I
understand it the way you explained it. I just have a hard time visualizing.
visualizing it. What does that one look like?
Number 9, the direction of the cross product. In which figure, which vector is in the direction of the cross product?
Oh, yeah. Okay. And is it those ones that we did earlier? Is it these two vectors? 1, 2, 3, and 5, 2, 1?
It's -1, -1, and 5, 1.
Or it's a series of.
Okay. -1, -1, and then what's the...
5, 1.
Oh, and they're just in the plane. Okay. 5, 1. Okay, so we're asked for unit vectors perpendicular to those in number 9.
Yeah.
And then in number 10, we're asked for which one is in the direction of the cross product of blah, blah, blah.
Yeah, you say which one is in the direction.
Okay. Well, if you take the cross product, you get -1.
So you're just asking which one is the direction of the cross product.
0, 0, 1.
0, 0, 1? Really? Wait, no, it's not. Oh, for a unit vector. The unit vector is 0, 0, 1. And that's what you, okay, so, yeah. Okay, so first take the cross product, so -1, -1, 0, crossed with 5, 1, 0, gives you 0, 0, positive 4. And so the unit vector is 0, 0, 1. And so 0, 0, 1 is the one that's in the direction of -1, -1, 0, cross 5, 1, 0. 0, 0, -1 is in the direction of the cross product 5, 1, 0, cross -1, -1, 0.
Oh, okay. So we don't say it's going right, left.
Nope.
So whenever it's in 2 dimension, you gotta include the.
Yeah, that's right. You always just put that z component in there, and the cross product is only going to have a z component.
So first I should find the unit vector of these two, and then find the cross product, and say the unit vector will be the direction of the cross.
Yeah, right. I mean, the way we did this calculation is we started by doing the cross product of these two and then found a unit vector in that direction. So this is the unit vector in the direction of that cross product. 0, 0, -1 is in the direction of 5, 1, 0, cross -1, -1, 0. Any other questions? All right, well, so we're heading towards Newton's laws. And I said last time, anytime you use Newton's laws, anytime you use Newton's second law or the moment equation, rotational Newton's second law, you need a free body diagram. I always abbreviate that FBD because I write it a lot, but remember that it's called a free body diagram. Otherwise, people laugh at you when you call it a full body diagram, or something like that. And I had a physics class where somebody called it a free base diagram. Please don't do that. I can get in a lot of trouble. Okay. So free body diagrams. So first, choose a body to isolate. It can be a body, it can be a collection of bodies. It can be a part of a body. It just has to be a lump of material that you could imagine separating from, it's an enclosed mass of material, okay? Something you could imagine shrink wrapping, you know? It has a surface all the way around. Second, draw a closed outline of the body. With no outside objects and no internal details. All you want is the outline. Okay, so for example, you want to do a Newton's second law calculation involving this car. Yeah. And this car has a cat sitting on it. You do have to be. That's most of what the grade is based on. Okay. Okay, so say you choose to isolate the car. Then it's going to look like this. Okay? Yes. And here are the things, but don't do it like this. No. So what's wrong with that picture? Well, yeah, let's say it was closed. That was just sloppy. Yeah, right. We're not isolating the grass, so that shouldn't be in there. Okay? You're like, that's a different car. That's the problem with this one. Not like that. What's wrong with this one? Yeah, the internal details. Okay? So the whole usefulness of a free body diagram is that the thing that it shows you is the boundary connecting, the boundary that separates your chosen thing from the rest of the world. Okay? So all we want is that boundary. One more. This is more common with, I should have done this as a person, but sometimes people do things like this. What's wrong with that one? It doesn't have, it's not an outline. There's no, like on this stick figure part, there's no way to see the distinction between what's included and what's excluded. Okay? It's not closed. It needs to be an outline. you want to be really clear about what that boundary is between the chosen part and the rest of the world. Okay. So that's step 2. Step 3, you need to draw all loads acting on the chosen object. And sometimes you can look at a picture and be sort of overwhelmed with this. Like, there's a lot of stuff going on. How do you know? How do you know when you're done? How do you know when you've represented every load that's acting on an object? There's actually a really easy way to do it if you're disciplined, careful about it. So all the loads acting on an object are just, first, field forces. In this class, that's just talking about the weight, the force applied by gravity. Although that also could include magnetic forces, electric field forces. But for us, it's just the weight. So first, draw the weight force acting on the object. And then second, just go around the boundary looking for places where the outside world makes contact. So let's say a contact force at each place on the boundary where the outside world and the chosen object touch. So, for example, going back to that car example, we have the weight, and then we have a force here. I'm going to say that we know the directions of these forces. I'll talk about how we know the directions of forces later, but I'll call that F1 because that's a place where the outside world, the grass, contacts the boundary. Then just keep cruising around the boundary and you get to another place where there's a force F2 where the grass contacts the boundary. Keep going around and you get to a place here where the cat contacts the boundary. Keep going around. There's nothing, 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 nothing. Get back to the original point, and now you know you're done. Okay? So when you get into complicated problems, just remind yourself of that. All you're doing is applying the weight force and then going around the boundary. Okay? These loads let me say, sorry about this. Let's say each load is either a load with a known direction or a load with an unknown direction. And which one of those we have determines how they're going to be represented in the diagram. What? Say it one more time.
Load direction.
Yeah. Sometimes we'll know it, sometimes we won't. And we'll have to treat them differently based on that. So first, loads with known directions. Draw an arrow in the known direction. And label it with a scalar variable or value. This scalar represents the magnitude of that vector. Of that load vector. So in the example I did up here, these are all, I treated these all as loads where we knew the direction. And you can tell that because I have arrows pointing in a known direction, and the associated variable or value is a scalar. It's a number. It's not a vector. Okay. So, for example, if you have a box hanging from the ceiling by a cable, the free body diagram of the box has a weight force, and then it has, since all a cable can do is pull on the object, this force is parallel to the cable, away from the body, and so that's a free body diagram of that box. Loads with unknown directions. Draw small coordinate axes, or really what you're drawing is small unit vectors aligned with the coordinate axes. Aligned with the coordinate system axes. And label these with a vector variable. So, for example, if you have a big object that's connected to the ground by a pin joint and leaning against the wall up here,
A big part of this class is knowing how to represent individual joints. We haven't done anything with that yet, so I'm just going to tell you that this pin joint applies a force with an unknown direction. This contact with the wall applies a force with a known direction. So the free body diagram looks like this. We have a force vector here that we don't know the direction. I'll just call that F. I said to do the weight first. I forgot to do that, but there's the weight. And then here we have a force with a known direction. I'll call it R, pushing from the wall. Any questions about those? All right, well, I'll finish talking about this next time. I'm going to post a few more vector problems for you since we're not on to the next stuff yet and you need something to do. But pretty soon we'll get into using Newton's laws. But for the time being, if you're really careful about these rules in this class, you'll be happy as the class goes on. So take some time, please, to read back over this stuff, try to make sense of what I'm talking about, remember this stuff, and it'll pay off. Okay.